Function notation is something possibly you've seen before, but if not, let's have a look at it. You can see here that we've got a linear function, the equation for a linear function there, and another way of writing y equals 2x plus 1 is f of x equals 2x plus 1. It means the same thing essentially, function of x. So x is part of a function, it's an independent variable in a function. So function of x, or f of x, is an example of function notation. So these two statements, basically, they're the same. F of 2 means we substitute in x. Well, for x we use 2. So f of 2 is how that's pronounced, and f of 2 would be the substitution of 2 in there instead of x. You can see that's what's happened here. The answer is 5. F of negative 4, for example, would look like that. And more generally, some other number, generalized, f of a would be 2a plus 1. So by incorporating this notation, we have an alternative way of writing the equations for functions. Writing these out formally then, if we were given the rule or the equation y equals x squared and the domain is all real numbers, this is how we would write this full statement in function notation. F of x equals x squared, where x is any real number. So that says where x is the element of real numbers. X is anything that belongs to real numbers, so it's anything that can be put on a number line. For the function y equals 2x minus 1, and we're given that domain, we would write that as f of x equals 2x minus 1, comma, which means where x is one of the elements from the interval 0 through to 4, and remember the square brackets are inclusive. If the domain is all real numbers, we often just write the real end. We have that implied domain or the maximal domain, which was mentioned briefly in a previous video and will be touched on again in a video coming up. This idea is pretty simple, so let's look at some examples which will further help you make meaning of this. If we're given f of x equals 2x squared plus x, find f of 3 in the first instance. So we would be writing f of 3 equals, now we do the substitution, 2 times 3 squared plus 3. So order of operations, square the 3 first, that's 9, times 2 is 18. 18 plus 3, which is 21. B, we've got f of negative 2 would be 2 times negative 2 squared plus negative 2. Okay, negative 2 squared is positive 4. Positive 4 times 2 is positive 8 plus negative 2, which is 6. We can do what's called composition of functions, as putting a function into a function, and that's an example of that one. It's f of x minus 1. So just keep following the same process. We're subbing that in. Instead of x, we've got x minus 1. Now you could leave it like that, or you could optionally do this. So it'd be 2 outside of x minus 1 all squared is basically x minus 1, x minus 1. Alright, whoops. Gone to the edge of my stylus. So that would be first term by the first term, first by the second, second by the first, second by the second, to expand that out correctly. So that would be okay. So we've got first by first is x squared, first by the second is minus x, and then and so on, and negative 1 times negative 1 is positive 1, and we still got the x minus 1, the second term there. And we've got 2 outside of x squared minus 2x plus 1 for 2 outside of it minus x minus 1 and 2x squared minus 4x plus 2. Now minus x minus 1 would be minus x plus 1 because minusing a minus makes a plus, and then on the last line there we just need to tidy up. 2x squared. Now we've got minus 4x and minus another x over there, so that's minus 5x. Plus 2 plus 1 is plus 3. Final example is f of 1 on a where a can't equal 0, so there's a restriction on the domain. Okay, so we've got to take heed of that because you can't divide by 0. That's the reason for that. So f of 1 on a. The last two are perhaps seem unusual, but you will get unusual things. So subbing it in, we still follow the same process. We've got 1 on a subbed in for x. It's 1 on a. And that is 2 times 1 squared over a squared. 1 squared is just 1 plus 1 on a. And we could go a little bit further. Basically we've got our answer, but we could make that a little bit more mathematically elegant by putting everything over a squared. So if we want to make this denominator, common denominator basically, okay, so we can put everything over a squared. If we make the right hand fraction 1 squared over a squared, so sorry, not 1 squared, we have to make that an equivalent fraction. Let me write it down here in a different colour. So we're turning 1 on a into an equivalent fraction over a squared. To clarify, I've divided the bottom, multiplied the bottom by a goes to a squared. We've got to do the same to the top to be an equivalent fraction. That'll be a over a squared. So that right hand fraction will be the same as a over a squared. Putting it all over a squared, then we have 2 over a squared plus a over a squared.